Stephen and I got to work together at the first part of the administration, and one of the things I just loved about Stephen was he was so committed to his staff and his people. And he would regularly call me about how we could increase their pay. And so, Steve, that's one way you get the attention, by being a good leader. And so, Stephen, thank you so much for your leadership. You know, in reading, if you look through the many biographies of Dr. Chu, you will find that he admits, or he at least claims, to be the underachiever in his family. Now, I don't know about your family, but in most families, winning a Nobel Prize and being Secretary of Energy would probably put you at the top sibling spot. But you can see the amazing family that he must come from. The second thing that strikes you about Dr. Chu is how generous he is in giving credit to the many teachers and mentors who developed and encouraged his love of math and physics. The people who gave him the freedom to experiment, explore, and is something that I know he talks many times about, even fail. And there's great learning in failing. He's giving back to his students in the same way. And as we strive to get more young women and men into the STEM fields, people like Dr. Chu, who teach and who mentor and who spark interest in science and math, are invaluable in that effort. As the first scientist to serve as the Secretary of Energy, Dr. Chu was responsible for implementing President Obama's ambitious energy agenda. He was given the task of increasing our investment in clean energy, reducing our dependence on foreign oil, and addressing climate change. And in his spare time, create a few million jobs. When President Obama announced Dr. Chu's nomination as Secretary of Energy, he said, quote, "The future of our economy and our national security is inextricably linked to one challenge, energy," end quote. Dr. Chu took that challenge very seriously. While he was Secretary of Energy, he was instrumental in pushing the development of alternative energy sources. Under his leadership, the United States doubled the amount of power generated by renewables. More importantly, he oversaw the opening of the ARPA-E, translated the Advanced Research Projects Agency for Energy and Energy Innovation Hubs. And ARPA-E has variously been compared to massive green venture capital firm and the laboratory where James Bond gets all of those amazing spy gadgets. So as the Q in this scenario, Dr. Chu gave the scientists and researchers at those ARPA-E labs the freedom that they had at Bell Labs. He gave them and all the Department of Energy employees the freedom to pursue solutions to our energy problems that were both high risk and potentially very high reward as well. Inspired by people like Dr. Chu, we are now working between the United States and Australia to bring out and increase that innovative spirit in all of us. I can think of few places on the world and the planet better than Australia to talk about solar energy. From government to academia to business, Australians are working hard to take advantage of one of your greatest assets, the Antipodean light. We are taking full advantage of it at our small United States Embassy mission here in Australia. Here in Canberra, we have put solar panels on all of our US government-owned diplomatic housing. Those panels now produce more than 180,000 kilowatt hours of electricity a year. They heat our water, and they have reduced our costs amazingly. In fact, we have received quite a few awards at the embassy, Stephen. I know you'd appreciate this, both for recycling, for energy saving, and our sustainability programs. And we are proud to be one of the greenest embassies here in Australia. But Australian companies are also looking into better and more affordable solar roofs, both for commercial and residential properties. Mining companies are building solar plants to replace diesel in their powering of their mines. In June, President Obama and Prime Minister Tony Abbott announced a cooperative effort between the National Renewable Energy Laboratory and the University of New South Wales and the Energy Change Institute here at ANU. Together, we will research the further development of solar voltaic technologies like tandem solar cells and thin film solar cells, which I know you'll hear more about today. We are so fortunate to have had Dr. Chu at the helm of the Department of Energy during a crucial time for the United States. Because of his excellent leadership, we are now closer to energy independence as a nation than we ever have been before. We now have more people employed by the solar industry than we do by the coal industry. And we have encouraged the talents and imaginations of some of the best and brightest minds for the future. Not content to rest on his laurels, or perhaps determined to finally become that family overachiever, Dr. Chu is continuing his impressive research now at Stanford. I'd like to tell you more about that, but as I tried to read through it, it was way undecipherable to me, Stephen, so I'm looking forward to hearing your talk today, and you'll hear it directly from him. I am so pleased that he was able to make his trip to Australia. He experienced a biking accident on his knee just shortly before he came, and it is a true testament to both his valor and his persistence that he made the trip, even though that serious accident. So, Stephen, we're so honored to have you here, and it's my great pleasure to introduce to you Dr. Stephen Chu.
So thank you, John, for that lovely introduction. I have to say, working with John was a real joy. If you didn't get his real title, let me translate it. He was head of HR for the US government. And usually when you have to deal with HR people, you cringe, the hairs in the back of your neck stand up and you say, oh, and you have to weather it. But John was very good. He was more than very good. He understood that what we would do in the government, what any organization do, really, it's all about the people and the quality of people and how to get the best people. And if you get the best people to come, how do you keep them there? And that's what it's about. You absolutely have to do things by the rules, fairly, all those things. But really, getting people to come and serve at the government. Not everybody is willing to take a factor of 5 or 10 cut in pay, as I did. And so that's why I was badgering him to say, maybe we can only ask him to take a factor of 3 cut in pay. All right, so let me just push on. And before I talk about solar, I have to put it in context. And for all of you in the audience, whenever you do something in research, you have to know what the competition is doing in research. And if you're in industry, you have to do that. So the question is, what is the competition doing? And one part of the significant competition is the fossil fuel, oil, natural gas, and coal. Oil and natural gas particularly are deemed very valuable because oil for transportation especially. And so let me quote 2 people I respect immensely. And they said, our ability to find and extract fossil fuels continues to improve, and economically recoverable reservoirs around the world are likely to keep pace with rising demand for decades. Well, I said that. Why? Let me just remind you of U.S. oil production from 1945 to 2012. This chart goes up to 2010, and you see that peak oil production in the United States was about 1970, and despite the Alaskan oil find, that orange stuff, it continued to decline. But then on the extreme right-hand side, there's this little green triangle called tight. This is so-called tight oil that could be released if you fractured it with water. And the following year, tight oil increased to so that the U.S. production is 7.5 million barrels a day. By the end of this year, it's going to be 8.5 million barrels a day. The increase in tight oil was about 4.5 million barrels a day, which is more oil than any other country in the world except three: Saudi Arabia, Russia, and the United States. More than Venezuela, more than Iraq, more than Iran, more than Canada, more than every other country, just the increase. And it can go higher. So what else is there? Well, there may be potential reserves of oil and gas that are perhaps 10 times larger than the rest of the world. And so where you see brown, you see potential tight oil and gas. Now, tight gas in the United States is no longer being explored actively. You've got high producing wells, and gas is now $3.50 to $4 a million BTU, about 1/3 to 1/4 is the rest of the world. And so, in fact, sadly, gas is being flared in North Dakota at a great rate because they want to get after the expensive good stuff, oil, and so they're just burning it because they're interested in short-term profits, not long-term, not total profits. And so this is a real tragedy. But the point here is that, for example, China may have 1.5 times more oil, tight oil, than in the United States, and there are many other countries around the world who do this. Russia, of course, is aghast at this new source of oil, and they have people around in Europe trying to convince the Europeans that this is really dirty, ugly stuff. It's threatening the water tables, and you shouldn't try to develop gas and oil in Europe. Russia has become a very environmentally conscious country in all countries except Russia. So let me also say, that although it's not on the topic, I do want to remind you something about the 800-pound gorilla in the room, and that is really climate change. But I'm going to introduce it in a slightly different way and only talk about it briefly. This is a graph of tobacco use in the United States from 1900 to 2005. And the black curve is the average per capita use of cigarettes per male adult. And by 1965, where it peaked, the average consumption of cigarettes was 220 packs a year, including non-smokers. We're a very smoking country, from essentially zero to very large smoking. And by 1950s and certainly by the 60s, that blue curve, that same cohort, adult males, dying of lung cancer. And it was beginning to rise considerably above the noise, and the medical community is saying, oh, wow, what's happening? There seems to be a correlation between cigarette smoking and lung cancer deaths. The tobacco company said, well, correlation does not mean causation, and since you can't predict who's going to get lung cancer, you don't understand the microbiology of how you get cancer from cigarette smoking, you can't prove it, so what's to worry until you prove it? Kind of sounds familiar. But nevertheless, the epidemiology pushed on, and by the mid-late 60s, they were able to put warnings on packages of cigarettes. The Surgeon General said, caution, cigarette smoking may be hazardous to your health. The next Surgeon General said, caution, cigarette smoking is hazardous to your health, and he was promptly fired by the next president. But never mind that. As we went to the 80s and 90s, a huge campaign to convince young people not to start smoking ensued, and you see that black curve just going down, 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 losing 60% of consumption per capita. And then you see deaths from cigarette smoking going down. I want to point out that there's a 25-year lag. A 25-year lag from the time the average person starts smoking to when they get lung cancer. So they do a lot of damage in this ensuing years. That's not to say if you've been smoking for 25 years and you haven't had lung cancer, you're safe. No. It's average. You can get it in 5 years or you can never get it. And so science today still can't predict that. We do know today that if you smoke, and this is very serious epidemiological studies to take all of the other factors that might distort the correlation, if you smoke a half a pack or more a day, you have a 25 times higher chance of getting lung cancer than if you didn't smoke. 25 times, not 25%. And smoking is the greatest cause of premature deaths in the United States that are preventable. We also know that coronary heart disease, stroke, 2 to 4 times higher. All right, so hold that thought for a moment. Here's some more data, 1850 to 2010. And you see on that top curve these wiggly lines, and it's the average land and ocean surface temperature. And to most people, you would say that those temperatures average over the Earth are increasing. Except a few people in DC, they look at that and they say, no, it's not increasing. Over the last 15 years, it's been essentially stable. That's true. If you cherry pick the data, the last 15 years, it's been essentially stable. We don't know why it's stable. We don't know why in around 1945 to 1970 you have this long plateau. We do know why and that's very complicated having to do with the ocean currents. I don't want to go into this, but certainly over a century, we do know if energy in is the same and energy out is less, there's only one way the temperature is going to go. Because you begin to average over all these subtle ocean currents and things. By the way, the lower curve is the rise in sea level. All right, so now we'll probably tell you something that only the climate experts will know about, and that is, it turns out that if the biochemistry, the chemistry of life is much more selective than inorganic chemistry. And if you're a plant and you take in carbon dioxide in photosynthesis to create the stuff that the plant needs, your preference of taking in carbon-12 is much better than, let's say, carbon being dissolved in the ocean. And so you're scarfing in carbon-12 and you're preferentially rejecting carbon-13, an isotope of carbon-12. All right. Now, you're a plant, you've got high levels of carbon-12 to carbon-13, yeah, you get fossilized, you go deep underground, you take it up, you burn it, all right? So there's less carbon-13 than carbon-12 when you're burning fossil fuel. And so you look at this difference, and this is called the Zeus effect, and here on the curve, let's see if you have a pointer. Where's my pointer? Somewhere by its pointer, but pointer is here. Okay, so this curve is carbon dioxide increasing from 1750, beginning of the Industrial Revolution to the present time, and the bluish curve, this thing over here, is carbon-13. This is carbon-13 over carbon-14. And so what you're doing is you're taking massive amounts of carbon that are pre-selected to be more carbon-12 than carbon-13, and you're throwing it back in the atmosphere. And so if you do that, you dilute the carbon-13, which is happening. Quantitatively, it makes sense. It's quantitatively in agreement with how much fossil fuel we burn since the beginning of the Industrial Revolution. There's another isotope, carbon-14, which is also an indicator. Carbon-14 is a radioactive form of carbon. It's made in the upper atmosphere with proton bombardment of nitrogen-14. Carbon-14 decays in 5,700 years. It mixes into the atmosphere, it's incorporated in all living things, you, me, trees, you name it. And suppose you die, and you've got a certain ratio of carbon-14 in your body. And they put you in a coffin for 10,000 years, make it 1,000,000 years, so that all the carbon-14 in your body is gone. And they dig you up and they put you in a fossil fuel power plant. Right? You're part of the new energy. And, you don't have any more carbon-14. So if you burn a lot of fossil fuel, you stick up stuff devoid of carbon-14. Okay? So it too gets diluted if it's sequestered for millions of years. And here you see the carbon-14 going down as the CO2 goes up. And you say, well, wait, you only showed us data to 1950, and so what's going on here? And what's going on is after the 1950s, there was a big perturbation on carbon-14. It was called atmospheric hydrogen bomb testing. And that was a big perturbation. And you see this green curve as the United States and the Soviet Union began to test hydrogen bombs. And they, on land in the atmosphere, this carbon-14 went spiking up like crazy. This oscillation, it actually went up to the stratosphere. The limit on the hydrogen bombs was actually defined by, we can make them bigger, but if we make them any bigger than 50 or 100 megatons, most of the energy just goes up into space. You've just blown too big a hole in the atmosphere. So, but they were testing bombs in the 5 to 10, up to 50 megaton range, and that's what was happening. These oscillations are actually the mixing time between the upper atmosphere and the biosphere. So this tracer carbon-14 allows you to mix it, and you see that since the testing was done in the northern hemisphere, it takes about 1.5 years for the northern hemisphere to mix. It takes a while for the carbon-14 in the atmosphere to be absorbed by the northern hemisphere ocean and the southern hemisphere ocean. So you see this is going down, this is going up, and then you see this above here, and so that you could say, well, most of it's now working its way into the ocean. No, it's declining too fast, and it too is consistent with the fact that you're burning lots of fossil fuel. You're throwing up carbon-12, devoid of carbon-14, because it was underground for millions of years, and therefore you're diluting the carbon-14. So both carbon-13 and carbon-14 are telling you there's a direct quantitative connection between burning fossil fuel and what we see. It's not a natural oscillation between the atmosphere, the land, and the ocean, because those natural oscillations don't do this isotopic mixing. Okay, so this is one of the reasons why scientists think that the carbon dioxide in the atmosphere that's shot up by about 45%, especially in the last 50 years, is due to humans. It can't be a nice natural cycling. So it's got human fingerprints all over it. It may be your imagination, you say, if you see lots of weird weather, storms, droughts, things like that. This is tracked by many people, climate scientists, it's tracked by insurance companies, and it's tracked by reinsurance companies. A reinsurance company is a company that insures insurance companies. If there's a big drought, as there was in Australia for a couple of years, or if there are massive hurricanes or typhoons, earthquakes, a standard insurance company may not have enough cash on hand to pay out the premiums, so they take out insurance. And so the reinsurance companies are particularly anxious about these big events, big weather events, and so they track them. They track tropical storms, floods, and a flood that causes a landslide, extreme droughts and temperatures and forest fires and crop failures. These are all things insured. And they have, what are the events that trigger insurance losses? And from 1850 to 2013, it's increasing. The only thing that was not increasing were the number of earthquakes. They small number statistics, but the earthquakes over that same period were bobbing along and they were steady. All these other things were increasing. So again, this doesn't prove that the warming temperatures are actually, it's a correlation. Now, the climate scientists say we can't predict hurricanes, we can't predict thunderstorms or tornadoes. We can predict we will see more extreme weathers, but it's a very imprecise prediction. So it's again like the 1950s or 1960s or 1970s in smoking. It's beginning to rise above the noise, all right? This is a cool thing that you should know about. These are two satellites, and they're very in a known polar orbit, and they measured the distance between these two satellites to a few percent of the width of a human hair. Why do they want to do this? As the satellites go around the globe, if there's an anomaly in the gravitational attraction of the Earth, it makes the orbit of the satellites bob a little bit. So you can imagine them going like that. And you measure the distance between them, and you can back out change in local gravity. And so there's a European pair of satellites, there's an American pair of satellites. There is on the books and in planning stage an upgrade to this based on actually cold atoms measuring gravity. And this can be done perhaps 100 times more sensitively than these guys. And so we'll see what happens, but let me just say what these satellites have been measured. From April 2002 to April 2012, this is Greenland. Can you see my pointer? You cannot see my pointer. This is Greenland over here, and this massive blue is a big loss in ice. And so if you look at certain glaciers over here, you see these glaciers, summer, winter, losing ice mass. And it's not only losing ice mass, but it's actually accelerating. Remarkably, you can do everything, but they're in polar orbit. They sample the entire world. This is the western part of the Antarctic ice sheet, again losing mass, and again accelerating. Okay. They also can measure water tables. Water table changes in California, water table changes in the Midwest, water table changes in India and Australia, and they're showing declining water tables. Now that's not all due to climate change. In fact, most of it is just due to water misuse. But they're doing that. All right, so let's go back to the analogy on smoking. Remember that 50-year lag? We don't know what the damage is that we've already done to the greenhouse gases, especially the carbon dioxide we've stuck up in the air. Carbon dioxide is pretty stable, but it's not 25 years. It's probably 50 to 150 years before it glides to the stop. Suppose we stop, that is to say, we stop emitting carbon today, what's the final temperature? It'd take 50 years, 100 years to find out. Okay, it's like all the mutations that you've been doing to yourself in smoking for the last 10, 20 years, and they're sitting there gathering. And actually, lung cancer is a multiple mutation disease. It's not a single point mutation. And so it actually requires constant injury to your cells. All right, so we don't know what the real damage is, and we don't know how long the CO2 will remain in the atmosphere. The estimates vary from a few hundred years to a few thousand years. All right, so let's go back. You're an adult, you smoke. Your decision, okay, whether you want to do that. The difference is here, we smoke and our grandchildren run the risk. And their grandchildren run the risk, because out to 1,000 years. And so far society as a whole has been saying, oh, unless you're 100% sure or 90% sure that all this bad stuff may happen, I don't want to give up smoking. And it's not my problem anyway. All right, so this, I think, is a problem. But it's a problem that society at large has never had to face in the history of humankind. Never has scientists said what we are doing today will affect what will be happening 500 years, 1,000 years from today. And it's invisible, and it's going to have to come out of the noise, and it could take a half a century to come out of the noise. So there are huge risks. We don't know exactly what will happen, but the risks are big. All right, another quote. The Stone Age came to an end not for lack of stones, and the oil age will come to an end, but not for lack of oil. That was said by Sheikh Yamani, a former Saudi oil minister. You're chuckling. You think that's why he's the former oil minister. No. What he meant is we transition to better solutions. So you go from the Stone Age to some Metal Age. And you need to transition to better solutions. If you don't find better solutions, and better solutions I mean economically better solutions, the oil, gas, and coal in the ground will be used. If it's the cheaper solution, it will be used. Because if you're Venezuela, if you're Russia, heck, if you're Australia, there's a huge temptation to just pump that stuff out of the ground because that's money. All right. So now, solar power. Well, let me just remind you that most energy sources are solar power. Of course, it's solar the way you think of solar PV or solar thermal, but wind is solar power. Hydropower is solar power because it's the sun that makes the water evaporate. Ocean currents are solar power. Fossil energy is solar power that had been stored millions of years ago. Fusion is solar power, and so is geothermal. It's a different kind of solar power. It's due to the ability of heavy elements when they radioactively decay to release energy. But let me remind you that when supernovae explode, they make a lot of heavy elements and radioactive heavy elements. And so it's a different form of solar power, but it's solar power. The only exceptions are tidal power. It's largely gravity gradients of the moon. And fusion power, not in the sun, that's clearly solar power, but terrestrial fusion power if we ever get it. Why is that? Again, to remind you, this is an incredible understanding of the early epochs in the universe, and this is time in seconds on a log scale. That's 1 second, 100 seconds, 1,000 seconds, 10 to the 4 seconds. And we're able to predict the abundance of the light elements due to what we know about physics and the early moments in the universe. And what we see is the time evolution of hydrogen, helium, deuterium, tritium, beryllium, lithium, and so on. The tritium all decays away. Deuterium is stable. The universe is 25% helium, a remarkable prediction. But all these other predictions have landed right on the money. Okay? But when we do fusion, what we do is we take beryllium and lithium, we breed it into tritium, we combine it with deuterium, and we make fusion. But where do we get that from? We get the beryllium and the lithium from the creation of the universe. So that's not solar power. So those are the reactions we use. It's heavy water and heavier water. This is hydrogen dioxide, tritium dioxide, and deuterium dioxide. It does weigh more. These are just scales. All right, so I went through this, I think. I don't know why good. That means my talk will be faster. Let me talk about things. First, before I do that, I just want to mention that about half of the carbon decrease will have to come from energy efficiency and should come from energy efficiency because energy efficiency is really the lowest cost option. It not only saves on carbon, but it saves money. And it just means that one has to do things in a smart way. But since this is a solar conference, I'm going to talk about energy and particularly solar energy. This is a chart of the dark blue or purple is the cost in the United States of various forms of energy. The cheapest today, and this is the cost of new sources of energy. If you want to put in a new gas plant and amortize over the lifetime of the plant 50 years or so, and the cost of natural gas and the operating cost of everything else, natural gas is the cheapest in the United States, and we're assuming that natural gas stays at $4 a million BTU. The Asian market is about $15 to $18 a million BTU. In Europe, it's about $15. The United States is anomaly low, and because of that, natural gas is the cheapest form of energy in the United States. Onshore wind is going to pass natural gas, including transmission of onshore wind, within 5 years. With the subsidy we have, it's cheaper than natural gas today by about 30%. That subsidy is going to be ramped down, turned off in the next couple of years, but for good reason. Wind doesn't need it anymore. In the next 5, certainly 10 years, it won't need it. Large solar PV, solar thermal, you see them up higher. Those lines there are wholesale electricity costs $50 a megawatt hour, $70 a megawatt hour. Very, very inexpensive. And the point here is that renewable energy, large-scale solar and onshore wind will get within few percent of that within a decade. Very, very good news. So that's where I think without subsidy, these things will be in less than 10 years. Nuclear is more expensive in the United States because unless we know how to build plants on time, on budget, and coal is significantly more expensive in the United States, and that's why we're no longer building coal plants. Natural gas is just too low a cost. What are the orange things? The orange things have to do with the actual cost to society of emitting carbon dioxide, depending on how you cost it, whether it's low, medium, or high CO2 costs. And so just think of the natural gas being shifted to the right by those blocks, or coal being shifted to the right and everything else. So the real cost to society in air pollution, and it's only a rough guesstimate of what the cost of society will be in climate change, you begin to shift everything to the right. So if you consider the real cost, they're already cheaper. But even without that, it's getting within striking distance. Solar, huge success story since the middle 70s, over the last 40 years. The price of solar modules has declined by about a factor of 40. There was this is called a learning curve. Every time you increase production shipments, deployment by a factor of 10, the price goes down by a certain fraction. Another factor of 10, it goes down by another fraction. As the cost comes down, the deployment increases. And so it's true of virtually all technologies that they follow a straight line if you plot it as the log of the shipments out and the log of the price. And but this doesn't follow a completely straight line, because there was a very attractive feed-in tariff started in Germany that actually drove the cost of solar modules down because it drew a huge demand, and so then you start to make more. But it also got a lot of people interested, particularly in China, so they started investing in multi-billion-dollar solar plants. And there was an overcapacity. There was a shortage of silicon, and the shortage of silicon made the price go up, and China got into the action, and there was an overcapacity, and the bottom fell out of the market. And so many large companies in Germany, a few in the United States, and a couple in China went bankrupt. The largest solar company in China went bankrupt. And so the bottom fell out of the market. They were trying to sell at below cost in this period down here because they had sunk costs, so they had to recover something. And the expression in those days was, well, you're losing every time you sell a solar module, but you make that up in volume. In any case, the market has stabilized over the last year. It will probably remain stable maybe for a year or two, but it will go down after that. Most manufacturers are making through this bulge, and they're still driving down costs. And so that green dot is where we think solar modules will be sold for at a profit, 50 cents a watt instead of $20 a watt. So that's a big change in reduction in cost. Right now, the solar manufacturers are making at cost, the manufacturing cost is 50 cents a watt today. And they're selling for 80 cents, so it's marginal profit. Okay. So we revitalized our solar program in the Department of Energy. We said, how good can things get? And so we started this in 2006 and 2008. We noticed that system prices, and the goal was to get solar to be comparable to natural gas without subsidy. We thought $1 a watt was realizable, and so we broke the cost down, starting in 2010 prices, which are over here. This is the solar module. These are the green is the solar module, the orange is the balance of the system, and there's a little sliver you can't really, the power electronics is that little sliver. And then we said, okay, how much can you really reduce things? And ideally, you could reduce them so that the module cost would be 50 cents a watt. This is a target of 2020. The balance of the system, 40 cents, and everything else, 10 cents. 50 cents, we're going to get there, absolutely, positively. When we put this out, the solar manufacturers said, you guys must be smoking something over there in the Department of Energy. And we said no, and we discussed it with them. And 2 years later, Dick Swanson, who's founded a very successful silicon photo company, said in a public talk, he said, it's unbelievable. The Department of Energy actually sat with us, told us how to think again about the business model, and then we decided they were right. And then everyone else decided they were right, and then it became a race to get those manufacturing costs down, and that's what's happening. So that's a good thing. I should say that module efficiency improvements is a big deal, because if you go, the polysilicon modules a few years ago was roughly 15-16% efficient. They're now going to 18-19% efficient. The silicon ones are now at 20, 21, 22% efficient. If you increase the efficiency, going from 15 to 20%, that's 3 over 15. That's a huge fractional change, and so the land use, the roof use, and the installation costs all scale. So everything else shrinks. So if you're in the solar module or solar cell technology research business, everything does scale with the cost of the efficiency, especially at rooftop. Another thing I want to point out, this is the solar spectrum at the top of the Earth. This is the solar spectrum at the latitudes, typically where you find land that makes sense to where you have solar. So this is not land in Upper Siberia. This is land in the United States and in Southern Europe and places like that. And so, looky here. This is where the visible light is, and all this stuff you can't see. And so there lies an opportunity to actually make solar films that keep windows mostly transparent, and you can still get a lot of energy if you can figure out how to do that. Lots of things are happening. The prices of silicon, polysilicon, telluride are jumping down like crazy. There's a new set of materials only in the last 10 years, perovskites, that is coming down like crazy. It's now at 15%, 18%, and there's a talk in this conference that described how you can use silicon, which will remain inexpensive for a very long time, with perovskites to get over 30% efficiency. And that's a pretty realistic goal. So that's all very exciting. For those young people in the audience, I'm going to remind you, I'm going to use an analogy on how solar works. Think of rain being those photons hitting a solar panel. And so your solar panel is this big bucket. And the rain goes in, and the photons come in, they create electron holes, and the electron holes are collected, and a voltage is built up across this. You've adjusted things so you can generate a voltage. A voltage related to water is a pressure. So you can get higher and higher voltage the more photons come in. But in the end, you want to tap that voltage, and you want to turn a little turbine, and so you want to drive things and produce energy. The bucket can be leaky, so that these precious photons or electron hole pairs can leak out in surface recombination. They can leak out as bulk recombination. They can do all sorts of things. But in the end, you're collecting this, you're producing a voltage, and you're using this current to generate something. Now, there's an optimum. How do you want to run the solar panel? If you have a large current, you say, I can really spin the wheel. But if you want to spin this wheel very fast, the voltage is very small, and then there's no pressure. Okay, so this limit's very inefficient. There's no pressure to actually force the turbine. If you throttle back, you have a very high voltage, but there's a little stream, and you can't really force the turbine. So there's this happy medium. And the happy medium, you can easily say, where its power is voltage times current. And you look at the voltage current curve of the photocell, and you find out how to maximize that. And in designing the photocells, that's what you're always thinking about. What is the voltage going to be, and what current can you sustain? But now, people who make photocells know this. And most of the people, the engineers and scientists who are in the photovoltaic business are thinking about all these things, clever ways, new designs, new materials, things like that. But let me tell you things that you might not be thinking about. I certainly was not thinking about it until I became Secretary of Energy. Here you have a solar cell, and then it's hooked up in series to another one, another one, another one. And so in series, you get a big high voltage between this solar cell panel and this solar cell panel. You take that DC voltage and you convert it to AC. And that's good because these electronics are pretty expensive, and they're actually less reliable than the panels. And so that's what happens. But imagine a leaf falls on theirs, or a bunch of clouds fall in this section of the solar panels, or maybe a defect in this panel. The current has to go through all of these. So the current through each of the panels is constant. If one of the panels is defective, or has leaves on it, or a cloud over it, it limits the current. And so all of them suffer. And so as a minimum, you want to have a converter for each panel, and then put them up and add them in parallel. And so up until very recently, that was not done. When you start doing that, you actually increase the efficiency of the solar panels by 20, 30, 50% in actual field use. People will not put a set of solar panels on a roof that has a partial shade. It just is not even worth it. All right? So here's the thing. What you'd like to do is divide these panels into subpanels, so that really inexpensive integrated electronics built into the panel can actually do the inversion, get it up to the voltage, so you don't have to do the series again. You don't have to use the whole panel. Panels are this big. And so if there's a defective part of the panel, it just gracefully gets out of the picture, okay? That's something in power electronics, but most electrical engineers don't know that this is a problem worth working on, or that they can be very, very rich if they solve the problem. So, listen, because this problem is eminently solvable. It is electronics, okay? And electronics we know how to do. You can start to unpackage what actually goes into the efficiency of a solar cell. These are the valence electrons. A photon comes in, and it promotes an electron up to the conduction band. You've got a hole down here, and it can be either from the top or somewhere down here. The hole quickly relaxes to the top up here, like a bubble coming to the surface, and the electron quickly relaxes the bottom here. So all those relaxation is just lost. But it's worse than that, because it also depends on the effective energy gap, not this energy gap, theoretical energy gap. And this effective energy gap actually likes it to have more intensity on the solar panels, okay? And there are other things. There's the fact, so if you, and this is a nice review article that unpackages all of these things. There's entropy losses, there's losses to all these things, and Carnot cycles, all this stuff. And so one of the things that good scientists are looking at is look at everything on the menu. Can you improve on these things? So it's just not a magic material list. It's all sorts of things, light trapping, ways of eliminating all this. So that's all good stuff. Now, let's see. Radical new ideas. Solar cells at high temperature don't work as well, because when you have high temperature, you create a lot of phonons, and the electron holes scatter from the phonons, and then they're lost. And so you're not, you know, in a hot desert where it's 40 degrees centigrade, and you've got the sunshine on it, there's a tendency to get warm, and so there's an issue of cooling the solar panels when they're hot. And so a number of researchers said, well, let's use this to our advantage. You can use in micro and nanolithography, you can make vacuums in here. And so here the photon goes in and it creates an electron hole pair, but you're also using the heat to make it more likely. The heat means that there's a thermal tail of these electrons, and you can make it more likely that you can actually get the electrons out. So it's a mixture of thermionic emission or heat-assisted photoexcitation. It's a new approach. There are materials that do this. Whether it's ever going to be competitive with silicon, I don't know, but it's there. So there are many things like that people are exploring. This is a solar map of the United States. Anything in orange and red, which covers 2/3 of the United States, has fantastic solar. Alaska is blue, and a little bit of orange is blue down here. It's not so good. It's comparable to Germany. But actually, now Germany actually is about 4 or 5% solar. And so even when the sun is not so good, it can be pretty effective. But in places, now Australia is actually, Central Australia is even better than this. You know, Australia is probably got the best solar reserves of anybody except possibly some certain sections of North Africa. What about installation of solar? It turns out that there are a number of companies, and these are some of the companies, SolarCity, Sunrun, SunPower, and they go and they knock on someone's door, it's happening all over California, and they say, we want to sell you electricity. You loan us your roof so we can put solar on your roof, but it's ours. You don't have to pay for it. If it breaks, we fix it. And we'll buy electricity from electrical companies, so you're guaranteed electricity, but you just sign a contract, 20 years, 15 years. If you sell the house, that's fine. There are ways to, you know, figure that out. And so that's all. You just loan us your roof, and we'll sell you. Let's see, if you live in Los Angeles and you are a medium user, instead of paying 15, 18 cents a kilowatt hour average, it's half the rate. The contract would be 9 cents a kilowatt hour. So, but you don't have no out-of-pocket expense. You're just paying for electricity. And so this new business model is made possible by two things. The fact that solar is becoming very, very inexpensive, especially in sunny places like Palo Alto or Los Angeles, Arizona, and the fact that there's what's called an investment tax credit. That company gets 30% of the investment it takes to buy the modules, the inverters, and install it back the first year. Okay. Now, the investment tax credit expires in 2016, the end of 2016. I think you should let it ramp down to 10% instead of 30%. In the United States, everybody gets 10%. But by 2020, I think for sure, you don't need any special privileges because it will be so inexpensive. And so that's another thing. So the modules are coming down, the inverters are coming down, but very slowly because we just need a bunch of smart engineers and more competition. But then there are things called soft costs, and they're not coming down very much at all. And so before I tell you what soft cost is, let me quote Min Lee, who's the program manager of Sunshot in DOE. Unlike physics, where we can fundamentally figure out the upper limit for efficiency of solar cells, there's no such limit to bureaucracy. And having been head of the Department of Energy for 4.25 years, I can absolutely attest to that. And so can John Barry. And what that means, it has nothing to do with the cost of the module, the electronics, and even the installation costs. It has to do with inspection fees, licensing fees, and all these other things. Right now, it costs about $2 a watt. $2 a watt means there's a certain panel of a certain size, a certain efficiency, and a certain illumination. So you're taking out whether it's in Germany or in Arizona or in Australia. You just say, this is the size of the solar panel and its efficiency. Costs $2 a watt to install in Germany. It's an online application. It's automated. There's a minor inspection after it's all done, but the county or the city doesn't inspect your roof before you install it and doesn't do things after you install it. They just inspect the electronics. In the United States, you have to have an online, it's not an online application, it's an in-person application. You stand on very long lines. You pay thousands of dollars, and then you have to pay the county inspector to inspect your roof to see if your roof is okay. And after they install it, then the county inspector comes out and has to inspect that your roof won't leak and it too is okay. And then someone else inspects the electrical hookup. And so the county makes several $1,000s on this. And so when I was at the Department of Energy in the last 2 years, we realized the soft costs are now 2/3. The installation, the non-module costs, are 2/3 the cost of solar on a rooftop. And the soft costs are coming to be 1/3. Well, that's crazy, I said. Why don't this city or this town or municipality say, make money the old-fashioned way? You need income. Do it with speed traps and parking tickets. Leave solar alone. This worked in Massachusetts, and suddenly the soft costs came down 50 cents a watt. And they're at $3.50. California, we couldn't make them budge, they're still $4. Okay? And they can go down another 50 cents. Just by saying, hey, don't view solar as a source of income for the city. But there's something else. because it was installation costs. So he said, well, of course German labor is more expensive than American labor. Not. So what's going on? So we videotaped them. Golly, they spent 1/3 of the time on the roof as American laborers. So I said, we can understand this technology and import it, okay? And what you do is you get someone skilled in putting the frame, and that's all they do. Boom, they're on to the next roof. And someone slaps on the thing, boom, he's gone. Someone puts in the wiring, boom, they're gone. They make it into an assembly line, okay? Instead of one person doing it all, oh, let's see, I gotta read the book, how do I do this now, how do you do that? And so they can install it much more quickly because they're using sensible business practices. In Australia, this is 2009, again, if you look at the key, this is the cost of the panel, this is the cost of profits, inverters, the racks, essentially everything else. In 2013, look at the cost of the panel compared to the cost of everything else. It's ridiculous, okay? So the inventors of solar panels were doing a great job. The inventors of installation were doing a lousy job. And the electrical engineers didn't know they should pay attention to inverters, okay, et cetera, et cetera, et cetera. All right, so in terms of policy, you have to look at the whole package in order to lower the cost. It's just not the solar panel. All right, so here's an energy quiz. Reliable electrical grid cannot tolerate more than 5 or 10% intermittent renewable energy. How many believe that once you go over 10% solar or solar plus wind, the show is over, in the sense it gets much more expensive? If you're at 10%, you need 10% more backup power, which should be included in the cost of the energy. So true. How many people think this is true? How many people think it's false? Okay. Well, the Hawaiian Electrical Company disagrees with you violently. In 2013, when the integrated solar in Hawaii was at 3 and 4%, but racing up rapidly because it was getting cheap. Cheaper than what? Well, Hawaii generates electricity by burning diesel fuel or bunker oil. It costs 39 cents a kilowatt hour for electricity in Hawaii. I don't know if you know what your rates are, but let me tell you, that's a high rate. And they said, no, the grid can't handle more than 2 or 3% average power. That means peak, it could be 8%. It goes unstable, and we're responsible for maintaining the grid. And a reporter from Forbes magazine was interviewing me about solar power and about stuff like that. And I was no longer Secretary of Energy, so I was released from remaining silent. And I said, well, that's just plain BS. I said, when it's 30%, yes, but not 3%. And a Hawaiian Electric Company got very angry at me. They may have taken a contract down on me, I don't know. But why was I so sure? Well, because there's what are called existence proofs in Europe. Germany is about 30% renewable, of which it's mostly wind with about 4% solar, and the other's bio. Denmark's 33%. Spain is 25%, 21% wind, 4% solar. Spain is not connected to the European grid in any substantial way. It's got the Pyrenees, and it's got French electricity not wanting renewable energy into France. So because of that, there's only a very thin tie. Spain is actually a standalone entity. Ireland is mostly a standalone entity. There are a few undersea cables, but not many. And so if you look down the list, and those green arrows are that list, and there you see on the left-hand side the fraction of renewables, 20, 40, 60, 80, 100%. Norway is actually over 100% renewables. It's all hydro. They sell their excess electricity to continental Europe. And those green arrows going down to 10% are those countries that essentially have no hydro pump storage or very little pump storage, no hydro power. So we're talking wind and solar, which are intermittent. And so we have existence proofs at 20, 25% that you can manage a grid without blackouts, brownouts, without load shedding. Now, these countries want to go to 50%. And they have to, at 50%, they have to start sharing energy. And at 50%, you actually have to start thinking of pumped hydro and batteries and all sorts of other things. But at 20, 25%, it's manageable, it's already been done. So that was the existence proof. If the policymakers and the regulators only listen to the utility companies and don't know about what's happening in some other part of the world, the utility companies say, we're the experts, we know, don't listen to these scientists or these environmentalists, they are just blowing hot air, then it is possible. But let me say that careful planning is essential for this. Once you go over about 10%, you have to actually plan it. You have to manage two-way flows. There has to be some way of doing some things. And once you're at 20%, it gets even more important. What is the careful planning? Okay. Suppose you're, let's say, 30% renewables. First, if you're a big country like Australia, you're good. United States, China, all perfect. All of continental Europe and North Africa are perfect. But take a single place like Australia, you have sun in lots of places, this wide area, so clouds over here don't affect something over here. Wind over here doesn't affect wind over there. But you need transmission lines to bring that to the other places. So transmission is actually becomes a big help for spreading out the variability. Load management is another big deal. Load management means you don't run defrost cycles in the middle of the day where electricity is most precious. A defrost cycle is you blow hot air into your freezer and you defrost with a little sheen, and then you recool your refrigerator. You do this at night when energy is cheap. If it's a really hot day and the price of electricity starts, the real cost of electricity, but you now begin to use all your spare capacity goes up, you want to do load management. You say, let your thermostats go up a little, stuff like that. You have to have automatic two-way flows. The United States does not have automatic two-way flows in the western part of the United States. When there was a blackout in San Diego, people were calling from one electrical district to another and say, hey Joe, got any extra electricity? Can you send me some? Okay? Or they would call up a hydroelectric dam and say, can you let some more water through because we lost the generating capacity over here. It was manual. It was manual by phone. In the 21st century, okay? And this should not be. Energy storage, starting with pump storage, but batteries are gonna get cheap. And then finally, the last thing is extra standby capacity. When solar becomes 50% or not solar, renewables, solar and wind, become 50, 60, 70%, that standby capacity is part of the cost of renewable energy. Let's make note about it. Even at 30% it is. All right. So now, why in the United States and in other countries are they fighting it? And let me say that if I were a utility company and I get yelled at if there's a blackout, I will want something where it's an old technology, I can turn up the power when there's demand and I can turn down when there's not demand. That's called fossil fuel. And to a certain extent, nuclear. But if there's demand and the wind stops shining, or the wind stops blowing and the sun stops shining, that's bad. And so you actually have to think a little bit harder. You have to actually think a lot harder. And if you're a utility company, a guaranteed monopoly, you have not gone into the utility business because you're a brilliant engineer, studied well at Stanford at the top of the class and say, I want to work for a utility company. You want to work for Apple and Google and Facebook? No, you don't want to work for PG&E. And so there's an issue here about the selection of the people who operate utility companies. But to be fair to them, it's a selection effect. Guaranteed monopolies don't usually breed the most innovative people. That's a kind of a Darwinism fact. And so it's up to think tanks, it's up to others, it's up to innovative utility companies to show that you can be more profitable if you think harder. Because in the end, it's the profit that's the motivation. And then if you're a regulator, you have to know about these existence proofs, deployed existence proofs. not some theoretical study done in a university. A deployed existence proof is the only thing that actually can convince a utility that it might be operational. And so that's also very important. Here's another quiz. I'm a professor, I give quizzes. Electric vehicles will never be cost competitive because of the high cost of batteries. How many believe this is true? How many believe that's false? Okay, it is false. But let me just tell you, we have in the United States a Tesla. But let me compare it to the Rolls-Royce Silver Ghost. Had the second longest production run of any car in the world, almost 2 decades. When it was introduced, it cost 1,500 pounds. 1,500 pounds, if you had a professional 10-year salary, could buy you one of these babies. And it was great. It actually got over 20 miles a gallon. It was a 7-liter engine that got 48 horsepower, but it was very smooth. It was a Rolls. And very quiet, very smooth, and it did this 15,000-mile run that showed it could last. It wouldn't break down. And so by 1911, the technology was there except for one thing. It was just too expensive. And by the way, the 7-liter, 48 horsepower engine was really a good thing in those days. Nowadays, 1 liter gives you 140 horsepower. Okay, and less emissions. So we have made progress. And so what really changed transportation was the Model T. It was the longest production run of any car in the world. And Henry Ford said, I want to make this affordable to the vast majority of Americans. And it was this Model T that took the United States from the horse and buggy whip era into the automobile era. So if you want to think electric vehicles, you can't think Tesla, which is without subsidy about $120,000 for the long-range version. You have to think $25,000 for a 300-mile version and charge in 20 minutes. You don't want to charge in 4 hours. And so that's the challenge. The cost of the battery, 2008, $1,000 a kilowatt hour. Tesla, 78 kilowatt hours, $78,000 for just the battery manufacturing. Okay, by 2012 it was cut in half. Now it's $40,000. Still a lot of money for a car you're selling for $120,000. Well, again, sans subsidy. And so in 2011 we set as a goal: can you make a manufacturing cost, an automobile battery pack, the whole unit, for $160 a kilowatt hour, not $500. And with that price, you can sell a car for 300 miles, a Tesla S-Range car for $25,000. And utility scale can even get $100 a kilowatt hour, because at $100 a kilowatt hour, it begins to be comparable to hydropower. And so that's for utility scale. How are we doing? We're doing pretty good. This is Bloomberg New Energy Finance projection, the solid curve. Those X's are the actual costs as we enter into, go past, the 2012, 2013, beginning of 2014, and the costs are coming down. The Tesla battery is actually 3% cheaper than the Nissan Leaf battery. And the Gigafactory will be down here, turning operational in 2017, 2018 at the latest. So the costs are coming down, and we're actually maybe faster than the Department of Energy target. Very, very exciting. Utility scale also coming down dramatically. This company is starting to put them into testing. Their target manufacturing cost is this, but that's for today's battery. Higher demand, they've got to have to last 30 years and without any maintenance to be utility scale. But these things are happening. There are 2 or 3 companies that think they can manage. I should say that there's new research going on. The other stuff was incremental research. When I got back to Stanford, I started collaborating with a professor, Yi Shui, in mechanical engineering. There he is. He's one of the star professors, rising professors at Stanford. And what we're working on is not a lithium standard lithium battery with a carbon anode or a silicon anode, and the silicon anode he developed, and this company is making these things, but a solid metal lithium sulfur battery where we think that the energy density could be 4 or 5 times greater. The charging rate conservatively can be, if it's some tricks, 8, maybe 10 times faster and much safer. And so you couldn't use lithium metal before. If you charge it too fast, you get dendrites and short out the battery. And this is an example of a paper we just submitted last week. Now this is the third paper where the open circles are what happens to a lithium metal, and the solid ones are what happens to this new method. We just stopped testing after 120, 130 cycles because that's a few months testing. And but there are several approaches. We're looking at all of them in parallel to see what will happen. Stay tuned. We'll know in a year or two whether you can get something that could be that $100 battery and be 1/4 the volume of the Tesla battery, and then 1/4 the weight. Okay, I'm going to skip about utilities and what always costs and all these other things. I just say that we need new business models. I will say that, especially in Europe, that summer-winter storage is a real issue. It's also true in the northern part of the United States. May not be true in Australia. But you can't rely on North Africa as your solar source, because if you get cut off from electricity due to some political instability in North Africa, the lights go off. And so, so people would not be willing to do that. But suppose, as we see, as I hope to convince you, that renewable energy, wind and solar, become cheaper, cheaper, cheaper. 20 years from today, it will be cheaper than coal and natural gas. As I said, in the United States, it's already cheaper than coal. So you have cheap electricity. If you can take carbon dioxide and you can split water cheaply to make hydrogen and combine those two things to make a liquid hydrocarbon fuel, then the problem is solved. Because you could put a liquid hydrocarbon fuel on a tanker and ship it anywhere around the world. We ship oil everywhere around the world, and the ship, it's $80, $100 a barrel. The shipping costs are a few dollars a barrel. And you put them in storage tanks, 90-day, 100-day reserves. So you have some energy security. Okay, that technology exists. Tanker fleets and storage tank exists. What doesn't exist is this ability to take cheap electricity and nighttime electricity and turn it into a liquid hydrocarbon fuel. If you do that, then the renewable energy problem, then I see 100% renewables and energy security and everything else. So that's the last thing we need. And let me just close by saying the part of the things I like least about being a Secretary of Energy is the press. They're venal, they're trying to trap me like gotcha. And eventually, I told the president after the election that I really enjoyed working with him. I'd love to stay 2 more years, but my wife had other ideas, and she was going back to California, and she said, Steve, no one's irreplaceable, not even you. And I'm going back to California. Okay, I'm coming. And so on February 1, I announced that I was stepping down. And on February 7, the following news story appeared. Hungover Energy Secretary wakes up next to solar panel. Now, I'm going to read you part of the byline. Washington. Sources have reported that following a long night of carousing at a series of DC watering holes, Energy Secretary Steven Chu awoke Thursday morning to find himself sleeping next to a giant solar panel he had met the previous evening. According to sources, went on to allege, I didn't even remember the manufacturer's name. According to the sources, Chu's encounter with the crystalline silicon solar receptor was his most regrettable dalliance since 2009, when an extended fling with a 90-foot wind turbine nearly ended his marriage. So I walk in and work, morning of February 7th. My head of public affairs comes to me and says, "We got to answer this." And I said, "Yes." We normally don't answer salacious news stories. It's just not worth it because then it creates a thing that press love. But so by noon, we issued the following statement. I just want everyone to know that my decision not to serve a second term as Energy Secretary has absolutely nothing to do with the allegations made in this week's edition of The Onion. While I'm not going to confirm or deny the charges specifically, I will say that clean, renewable solar power is a growing source of U.S. jobs and is becoming more and more affordable, so it's no surprise that lots of Americans are falling in love with solar. Now, there were limits to what they allow me to say, because I could say, regardless of your sexual orientation and things like that. But in any case, the future of solar looks bright. There's a huge amount of technology that can be developed. I urge everybody to pay attention to the whole problem, not only the guts of the PV, but the whole system, and not only the whole solar system, but how it integrates with the current transmission distribution system, and know that batteries within 5 to 10 years at the outset will become very, very inexpensive. That can do peak shifting from noontime to 4 to 10 o'clock at night. And all these things are happening within a decade. Most of the distribution systems are not planning for it. And you have to plan for it because you need some serious technology in order to capture the low-cost solution. Otherwise, we don't do the low-cost solution. We do the more expensive solution. And the low-cost solution includes all that other residual grid coordination stuff. So anyway, with that, let me conclude, and I'm not sure what else I'm supposed to do.